Welcome back to the series on topology. In today's video, we'll be talking about some notions related to the convergence of sequences. In particular, we'll be defining what a limit point of a set in a topological space is, and we'll be defining what it means for a subset to be dense in such a space. And finally, we'll move on to the definition of convergence in a general topological space. You can find a playlist with all the videos in this series by clicking the info card that should appear right now. Let's get started with our first definition. Suppose that X is a topological space and A is some subset of that space. In that case, we call a point P in X a limit point of A if every neighborhood of P contains a point of A other than P itself. Remember that a neighborhood of a point is defined just to be an open set that contains that point. Pictorially, the situation is as follows. So we have some large space X, and then we have some subset A of that space. So we take some point P in X, which may not lie in A, but could be very close to the set A. So this would be P. Now, to check whether this is a limit point or not, we need to consider all the neighborhoods around P and see whether they intersect A in a point other than P itself. For example, P might have a large neighborhood like this, and clearly this would intersect the set A in at least one point other than P itself. However, the definition requires that this hold for every neighborhood of P, so even if we make the neighborhood really small around P, it would still have to be the case that there is some point of A inside this small neighborhood that is not P itself in order for P to be a limit point. Here we could imagine that P is a limit point because it's located very close to A. However, if we chose some other point, let's say U over here, then this point U might have a neighborhood that does not intersect A at all, and in that case U would not be a limit point of the set A. You may be asking what's up with this condition that the intersection has to be with a point of A other than P itself. And this can be illustrated by the following example. So if we suppose that this orange point out here, which I'll call small a, is actually part of the subset A, then we could ask if this point small a is actually a limit point of A. Previously, we were just considering points that were outside of the set A, but now we're considering a point that lies within the set A. And this could also be a limit point if it fulfills the condition in the definition. So let's suppose that this small a has this pink neighborhood. Now, in order for A to be a limit point, it has to have the property that every neighborhood of small a would have to contain a point of A other than small a itself. Now here's where this extra condition comes in, because this pink neighborhood indeed does contain a point of A, because the point small a is part of A itself. However, it doesn't contain any other points of A. Hence, in fact, small a is not a limit point of A. On the other hand, if we were to choose some small b that's located within sort of the bulk of this set A, then we could again consider neighborhoods of B. And here, if the neighborhoods aren't very strange, it's clear that any neighborhood of B would contain some other point of A besides B. And so some point of A on the inside of this shaded region would be a limit point of A. However, the point small a that's isolated from the rest of the set A would not be a limit point. Okay, so that's schematically how we should think about limit points. The important thing to remember is that a limit point can be any point in the space, and it's relative to some set. And there's this condition that if we check for intersection with that set A, then we have to disregard the point itself. For a concrete example, let's consider the open interval 0, 1 on the real line. So that's 0, 1. And now we can ask what the limit points of this set are. So I'll draw a picture. So we have 0 and 1 excluded, but everything in between is included in this set. Now if we take some point inside the open interval, for example this point x here, then in order to determine whether x is a limit point or not, we need to look at the neighborhoods of x. So we let, let's say, u be some arbitrary neighborhood of x. And u might actually be a very complicated set. So it could, say, include this part, and it might have some other part here, and it might have some part here. So it just has to be an open set that contains x. For example, it could be a large union of small open intervals. So this would be our neighborhood U. Now, by the way that the open sets on the real line are defined, so that's according to the topology induced by the Euclidean metric, we know that we can find for each point in this set U a small epsilon ball which still fits completely within U. So in particular, we'll be able to find a small epsilon sized interval around x that still fits completely within U. Hence we can actually just consider such a small interval around x. So that would be something like a small stretch there. Now the question is whether this intersects our set of interest, so this open interval 0, 1, in a point other than x. Why would this be the case? Well, if x is not too far towards either 0 or 1, then this epsilon ball we've drawn around x could lie completely inside the open interval 0, 1, and in this case we could just take a point in that interval that's not x. For example, we could move like epsilon halves to the right or to the left, and then that would be a point other than x that is contained in the interval 0, 1. There's kind of an annoying edge case where x could be really, really close to one of the endpoints of our open interval. So suppose that y was really close to 0, and we've found some small epsilon-sized interval that fits completely within the neighborhood that we've chosen around y. So that would be something like this. Now it's possible that if y is really close to the endpoint, then this interval actually could reach out over the end of our set 0, 1. In which case, if we were to move, say, epsilon half to the left and take that point, it might not actually be a point in the open interval 0, 1. However, because the interval 0, 1 is open, there's also going to be a small, let's say, delta interval around the point y, which lies completely within the interval 0, 1. So this would be like a small delta in purple. And this is definitely in 0, 1. And then we could just intersect the interval we found that fits within the neighborhood of y with this small delta interval, and we would get another open set which lies within 0, 1 and is non-empty. In particular, we could also just go like delta halves to the right or to the left and find some point other than y inside this delta intersected with the epsilon interval. Technicalities aside, I think it's pretty clear from if you just think about how you would obtain some point other than x if you just go a little bit to the left or a little bit to the right, that this should be possible. Okay, so we've shown that any point inside this open interval 0, 1 is a limit point, and now we can ask if there's any other limit points. So let's redraw our situation. So we have 0 and 1, and we were considering the open interval between 0 and 1. Now if we think about limit points that lie outside of the open interval 0, 1, if we go far to the left, let's say somewhere here, then we can find some neighborhood of this red point, for example, this small open interval that is completely disjoint from our interval 0, 1. So this red point would not be a limit point. And in fact, as long as we have some positive distance between some point and either the 0 or 1, so either 0 from the left or 1 from the right, then we can always find such a small epsilon interval around the point that is still disjoint from the interval 0, 1. Thus, really the only candidates that remain that are not included within the open interval 0, 1 are the point 0 and the point 1 themselves. And in fact, both of these are also limit points of the open interval. Why is this? Well, if we have some open set surrounding the point 1, for example, then we can find a small epsilon interval that fits completely within that open set. And now, because this interval has a non-negative radius, it has to intersect the open interval 0, 1. So as soon as we're slightly smaller than 1, we're already intersecting the interval, and there will also in particular be a point other than 1 in that intersection, and that shows that for every neighborhood of 1, we have a non-trivial intersection with this open interval. Therefore, in this case, the limit points are actually the closed interval 0, 1. Next, we turn to the opposite concept, which is that of an isolated point. For this, we again let X be a topological space and A be some subset of X. And then we say that a point P in A is an isolated point of A if P has a neighborhood, and say U in X, that whose intersection with A only contains that point. This was basically the situation we had before, where we considered X and some subset A, and then we had this one point that was just by itself small a. Now if small a is an isolated point, then it has some neighborhood around it, such that, so this was U, such that if we intersect U with A, the only contents of that intersection is the point itself. So in this case, this would be fulfilled. Notice that here the point has to lie within the subset A. To illustrate this, let's consider another example. So we look again at the real line. So we have 0 here and 1 here. And now instead of taking an interval, we take a subset, which is a sequence, namely the sequence that's 1 over n for all positive integers. So the set B contains 1, then it contains 1/2, it contains 1/4, 1/3, and well, the points always get denser as we approach 0, but they never actually reach 0. We can now ask what the limit points and the isolated points of this set are. Now the name limit point is suggestive because, well, we can think about the limit of this sequence 1 over n as n goes to infinity, and that limit is 0, so we might try to think if 0 is a limit point of the sequence, and in fact this is the case. So if we look at 0, and we take any neighborhood of 0, then again we can find some small epsilon interval within that neighborhood that still fits completely inside it. So that would be what I'm drawing in orange. And now the question is whether this intersects B in a point other than 0. Well, 0 isn't part of B, so the question is really if it just intersects B at all. But this is the case because of the Archimedean property, namely that, well, the natural numbers are unbounded, and if we take 1 over n, then we can get arbitrarily small values for that number. This means no matter how small this epsilon is, because epsilon is a positive number, we can find some n in the natural numbers such that 1 over n is going to be strictly smaller than epsilon. And this point will lie inside this epsilon interval, and hence we have some point in the intersection. All right, so we found one limit point. Now we can think if there's any other limit points. Well, if we're strictly negative, so if we're strictly less than 0, then we can always find some small epsilon interval that doesn't intersect any positive number. So that's not going to work. And if we're somewhere between 0 and 1, then we can always find, for example, if we were to look at some point that doesn't lie in B, then we can always find some small epsilon interval around it that doesn't include any of the numbers that occur in B. So none of these points could be limit points. We can now turn to the points in B because we've seen that all the points outside of B aren't limit points. So what if we take, for example, 1/3? Is this a limit point of the set B? Well, if we have 1/3, then we can find some small epsilon interval around it that doesn't contain either 1/4 or 1/2. And so the only point in the intersection of this small epsilon interval, which is a neighborhood of 1/3, is 1/3 itself. Now this is precisely what is required for the definition of an isolated point. So 1/3 is actually an isolated point of B. Now the same thing holds for any point in B. If you choose some arbitrary point, there's always going to be some positive distance between it and its two neighbors in the sequence. And so we can find some epsilon interval around it that doesn't include those points. And this epsilon interval will be an open set of the real line that contains the point, so it's a neighborhood, and if we intersect it with the set B, we get back only that point that we've chosen. So in fact, every point of B is an isolated point. So here we have an example where the limit point of B, the only limit point of B doesn't lie within B itself, and every point of the set B is actually an isolated point. Finally, notice that the definition of an isolated point is actually just the negation of the definition of a limit point if we assume that the point is within A. So in the definition of a limit point, we're requiring that every neighborhood of the point intersects A in a point other than itself, and in the definition of an isolated point of A, we require that the point has a neighborhood that intersects A only in the point itself. This means that any point of a set A is either a limit point of A or an isolated point of A. Now we turn to a property that holds for subsets of a topological space, namely denseness. So we say that a subset A of a topological space X is dense in X if its closure is equal to all of X. Now the standard example for this is the rational numbers within the reals. So if you have the real line, then the rational numbers, well, they don't quite fill out the real line. So no matter how far you zoom in, there's an infinite number of rational numbers in your view. However, there are sort of gaps. For example, square root of 2 isn't a rational number, so there's a gap in the rational line compared to the reals. However, the rationals are dense in the real line, because if we take their closure, then we get all of the real numbers. Remember that the closure of a set was defined as the intersection over all closed sets that contain the set, and we saw in a proposition that being in the closure is equivalent to the fact that every neighborhood of that point contains a point of the original set. So we have that X being in the closure of Q is equivalent to the fact that every neighborhood of X intersects Q. This property is certainly the case for any point in the rational numbers, because if we take some neighborhood around such a point, it will include that rational number which we chose, and so that rational number will be in the intersection of Q with that neighborhood. However, it is also the case for any number in the reals without the rationals. So if we take some point X in the real line, you can imagine a zoomed in view, and we have some open set that contains X, then we can find some small epsilon neighborhood that is still contained completely within our original neighborhood. But now there's some positive distance between X and X plus epsilon, and one can show that there's always going to be a rational number sitting within that distance. So there's always going to be some R in Q that has distance less than epsilon from X. And this R will now show up in the intersection of the neighborhood with Q. So essentially the fact that we can approximate any real number by a rational number to an arbitrary degree of precision means that the rationals lie dense within the reals. Now the argument that I gave before for showing that the rational numbers are dense within the reals, it generalizes to the following proposition. So it says that a subset V is dense in X if and only if every non-empty open set C in X contains a point of B. I'll just quickly sketch the proof, but it's pretty similar to what we did before. So for the direction left to right, if B is dense in X, then by definition the closure of B is equal to X. So now take an open subset C of X that's non-empty. Well, then C is some neighborhood of a point in C. So for example, we could say C0 is an element of the C, and C is now a neighborhood of this point C0 in C. But we also know that, well, C is a subset of X, so C0 is actually also an element of X. But now because X is equal to the closure of B, again by a proposition we saw in the last video, C0 is in the closure of B if and only if every neighborhood of C0 contains a point of B. But the closure of B is just X, and we know that C0 is in X, so every neighborhood of C0 contains a point of B, but C is a neighborhood of B, so C must contain a point of B, and that's exactly what we wanted to show for this direction. Now the other direction also follows pretty much immediately from this proposition. So we suppose that every non-empty open subset C of X contains a point of B. And now we want to show that the closure of B is equal to X. So for this we just let X be some point in X, and now we need to show that it's in the closure of B. But by our proposition, being the closure of B was equivalent to the fact that every neighborhood of X contains a point of B. So we just let U be a neighborhood of X. And now we need to show that this neighborhood U contains a point of B. But U is an open subset of X. And it contains small x, so it's non-empty, and hence, by assumption, it contains a point of B, and, well, that's what we wanted to show. So this implies that X is, in fact, in the closure of B, and so every point in our large space, X is in the closure of B, and because B is a subset of X, and its closure is a subset of X, it means that, actually, B closure is equal to X, and that's the definition of B being dense in the set X. Finally, let's turn to convergence of sequences. We suppose that X is a topological space and that X sub I is a sequence of points in that space. Moreover, we have some point X and X, and we say that the sequence converges to the limit X if for every neighborhood U of X there is some natural number such that all the members of the sequence lie within that neighborhood for all indices greater than that natural number. This is essentially the same definition you're probably already familiar with for convergence of sequences in Euclidean space, but instead of having small epsilon radii, which form epsilon balls, we're just taking arbitrary neighborhoods of the limit in order to check whether a sequence converges towards the limit. So the picture for this is we have some sequence, which I'm drawing in red. And then we have some point which we think might be the limit, which is this point in purple, called that X. And now if we want to check whether the sequence in red actually converges towards X, we need to look at every neighborhood of X. So we take some neighborhood U around X. And for this neighborhood, it has to be the case that eventually all of the members of the sequence are within this neighborhood. So as of some index, so in this case, we might have this being x1, this x2, x3, x4, but after index 3, all of the members of the sequence lie within this neighborhood U. Hence, for this neighborhood, the condition would be fulfilled. We could set capital N to be 4. But in order for X to be a limit of the sequence, this has to hold for an arbitrary neighborhood of X. So even if we choose a very, very small neighborhood around X, then as of some point in the sequence, all of the members have to lie within this small neighborhood, which maybe we call V. So this is how we talk about convergence in the case of a general topological space. In contrast, if we think about convergence in R2, what we're doing there is pretty much the same thing. So if we have the same sequence in R2, then instead of taking arbitrary neighborhoods, we're just taking balls of radius epsilon. And we're saying that for every epsilon, if we take some epsilon radius, and we take an epsilon ball around that radius, then there has to exist an index such that for any index larger than that index, all the members of the sequence lie within that ball of radius epsilon. Now, the definition we just gave in terms of arbitrary neighborhoods may seem more general, but in fact, for the case of Euclidean space, these definitions are actually equivalent. Let's get some practice for this definition by thinking about the following proposition. For this, we have a subset A of a topological space X, and we have some sequence that consists of points of that subset A. And moreover, we assume that the sequence xi converges towards a point X. And we want to conclude that the point X is in the closure of A. I'll just sketch the proof by means of a picture. So if we have our space X and we have some subset A of X, and now we consider a sequence of points in A that converge to some limit. So let's say this red point here is the limit. Now we want to show that the red point actually lies within the closure of the set A. And for this, we again use this useful proposition for the characterization of being in the closure in terms of neighborhoods of the point. So remember that a point X is in the closure of A if and only if every neighborhood of it contains a point in A. All right, so let's take some arbitrary neighborhood around our limit x, this would be u, and now we need to show that it contains some point of a. But we know that the sequence of points xi converges towards x, and by definition this means that as of some index, all of the points in the sequence actually lie within this neighborhood u. But by assumption, our sequence of points, well, they're points of A, so in particular, there's going to be, well, one point of A that lies within the neighborhood. I mean, in fact, we have infinitely many points of A that lie within the neighborhood, so we can just choose one. And because this holds for every neighborhood of the point x, because by the definition of convergence, we have this property for any neighborhood, it means that x is actually in the closure of A, and that proves the proposition. Okay, so that's all I wanted to say for this video. In the next video, we'll be looking at continuous maps between topological spaces, which is perhaps the most important topic in this course.